Usually, when we architect a standard software system, there's an expectation of a strict boundary, a binary separation.
Right.
You have your processor doing the active dynamic computation, and you have your database handling the static memory retrieval. Compute is compute, and storage is storage.
Exactly.
But if you step into the world of modern large language models, suddenly that database is just entirely gone. We are looking at this architectural landscape for you that basically forces the processor to memorize the entire database inside its own logic gates.
Yeah, and it is the absolute definition of an architectural bottleneck. I mean, we are taking highly expensive dynamic neural pathways and forcing them to simulate what should be a straightforward $1 database lookup.
Which is wild.
It is. For anyone working with transformers, we have largely accepted that to scale capacity efficiently, well, we just rely on conditional computation, specifically mixture of experts, or MOE.
Right.
MOE allows us to drastically increase our parameter count without, proportionally increasing the active FLOPs per token.
Which brings us to the core of today's deep dive. We are unpacking a highly technical paper from Peking University and DeepSeek AI. It's titled Conditional Memory via Scalable Lookup, a new axis of sparsity for large language models.
Oh, it's a fantastic paper.
It really is. The authors highlight a fundamental inefficiency in that exact MOE paradigm you just mentioned. Modern transformers just completely lack a native primitive for knowledge lookup.
Yeah, they have no native database.
Right. To retrieve a static fact, they have to route it through dense layers or MOE experts. So our mission today is to deconstruct how these researchers solve this by introducing Engram. It's a conditional memory module that modernizes classic nologram embeddings for O1 lookup.
And we are also going to get into the sparsity allocation scaling law they discovered.
Yes.
Because that optimizes the trade-off between neural computation and this totally new static memory.
Okay, let's unpack this. Why exactly is using attention and feed-forward networks for memory such a structural flaw?
So to understand that, we have to look at what the authors call linguistic duality. Language modeling inherently requires two qualitatively different subtasks. On one hand, you have compositional reasoning, parsing complex grammar, following logic, synthesizing novel ideas. That requires really deep dynamic computation across the residual stream.
And that is exactly what attention mechanisms are built to handle, right? They map those relationships dynamically.
Exactly. But on the other hand, a massive portion of natural language is just local, static, and highly stereotyped.
Like named entities or idioms.
Right, formulaic patterns. The paper actually provides this brilliant mechanistic example of the inefficiency. Take the entity, Diana, Princess of Wales.
Okay, a very standard static entity.
Exactly. In a standard LLM, resolving that multi-token entity requires consuming up to 6 early layers of attention and feed-forward networks.
Wait, 6 layers, just to assemble the name.
Just to assemble the concept. The model has to progressively compose those features across the residual stream. It is basically running an expensive runtime reconstruction of a static lookup table.
Man, it's like using a state-of-the-art physics engine to calculate the molecular friction of a bouncing ball every single time it drops, instead of just, referencing a pre-computed lookup table.
That is a perfect analogy.
You're just burning active FLOPs on something that has not changed since the last time you saw it. And because standard transformers lack that lookup table, they are forced to dedicate early layers to static reconstruction instead of allocating them to higher level reasoning.
Which fundamentally limits the network's capacity for complex logic.
Right.
So the Engram architecture solves this, but...
Wait, I have to push back here for a second.
Sure.
Not-grams are a really ancient NLP concept. How exactly do we integrate a static Oder-Lazo lookup into a dynamic multi-branch transformer architecture? Doesn't that risk breaking the gradient flow or just introducing massive amounts of hash collision noise?
Well, that is the major engineering hurdle, and Engram overcomes it through 2 distinct functional phases, retrieval and fusion.
Let's start with the retrieval phase, specifically the tokenizer compression. Because standard subword tokenizers like byte pair encoding, they're optimized for lossless string reconstruction, not semantic density.
Right, exactly.
They assign completely disjoint IDs to semantically equivalent terms. For instance, capital A apple, lowercase a apple, and space apple all have totally different token IDs.
Yeah, and in an anagram table, that leads to massive fragmentation of the exact same concept.
So how do they fix it?
To fix that fragmentation, Enneagram introduces a vocabulary projection layer. It acts as a surjective function, basically mapping those raw token IDs into canonical identifiers based on normalized textual equivalents.
Oh, interesting. So how much does that actually shrink the space?
In practice, for a 128K tokenizer, this projection reduces the effective vocabulary size by 23%.
Wow.
Yeah. By collapsing the semantic space, you significantly densify the representation before you even attempt to hash it.
But even with the 23% reduction, the dollogram combinatorial space is still, like, functionally infinite.
Yeah.
You cannot parameterize every possible combination of tokens. You need a hashing mechanism that scales without blowing up your memory footprint.
And they utilize multi-head hashing for that. For each nologram order, they use $2 distinct hash heads. Each head employs a lightweight multiplicative XOR hash.
Multiplicative XOR. Why that specifically?
Because it maps the compressed context to an index within an embedding table so efficiently, it mixes bits far better than simple addition or linear probing.
Ah, so it ensures a highly uniform distribution across the indices.
Exactly. By concatenating the retrieved embeddings from all these independent heads, the system effectively mitigates the collision issue and forms a really robust final memory vector.
Okay, but retrieving the exact token embedding is only half the battle, though. You now have a completely rigid static vector.
Yeah.
If you just blindly inject that into the dynamic flow of a transformer, you risk derailing the context entirely, especially if the word is polysemous and has multiple meanings, or if you still encounter residual hash collisions. So how are they preventing that static vector from overriding the model's contextual reasoning?
Well, this is where the fusion phase comes in. What's fascinating here is how Engram utilizes a context-aware gating mechanism inspired by attention.
Okay, how does that work?
To handle polysemy and filter out irrelevant retrievals, Engram uses the current hidden state of the model as a dynamic query. Keep in mind, this hidden state has already aggregated global context via the preceding attention layers.
Right, it knows what the sentence is actually about.
Exactly. So the retrieved static memory serves as the source for both the key and the value projections.
And they compute a scalar gate, alpha t, bounded between 0 and 1. But standard dot product attention can cause logits to scale exponentially with hidden dimensions. If you just take the dot product, wouldn't the gate easily saturate at 0 or 1 way too early in training? That would completely kill your gradient flow.
It absolutely would, which is why, to ensure gradient stability, they apply RMS norm to both the query and the key before computing that scalar gate.
Oh, wow. Applying RMS norm keeps the pre-activation values bounded.
Exactly. So if the retrieved static memory contradicts the current global context of the hidden state, that scalar gate smoothly approaches 0 and the noise is just completely suppressed.
So it functions as a dynamic relevance filter that enforces strict semantic alignment. That is incredibly elegant.
It really is.
And the architecture gets even more interesting when we look at how it integrates into a multi-branch backbone. They use manifold constrained hyperconnections, or MHC, with 4 parallel branches.
Right, null equals 4.
But integrating a sparse lookup into a parallel branch architecture typically creates a severe memory bandwidth bottleneck.
Yeah, it does. So to balance efficiency and expressivity across those branches, Engram employs a highly specific parameter sharing strategy.
Right.
A single sparse embedding table and a single value projection matrix are shared across all 4 branches. However, they use 4 distinct key projection matrices.
Wait, so the branches share the underlying factual knowledge from the value matrix?
Yes.
But each branch maintains its own independent gating behavior through its unique key matrix.
Exactly. It can route that factual knowledge differently based on its specific representational manifold.
Mathematically, that setup must be brilliant for hardware utilization.
Oh, it is. It allows the linear projection, so the 1 value matrix and the 4 distinct key matrices, to be fused into a single dense FP8 general matrix multiply, or GEM.
Which maximizes the compute utilization of the tensor cores on modern GPUs while still allowing for that branch-specific dynamic gating. Okay, so we have established the mechanics. Engram is mathematically sound. It preserves gradient flow via RMS norm. It suppresses collision noise via multi-head hashing, and it optimizes GPU utilization via FP8 fusion.
Right.
This brings us to the core architectural problem for you, the practitioner tuning a frontier model. If you have a fixed parameter budget of, say, 10 billion parameters, you are faced with a strict choice.
Yeah.
Do you allocate your inactive parameters to routed MoE experts, or do you allocate them to this new Engram memory?
And the researchers formalized this as the sparsity allocation problem. They established a strictly controlled environment constrained by isoparameter and ISO-FLOP's metrics.
Meaning the active parameters per token, PLOP, which dictates training and inference compute costs, is kept strictly fixed.
Right. The variable is a PS, also the inactive parameter budget. They define an allocation ratio, rho.
Okay.
If a rho is 100%, you have a pure MOE model. All inactive parameters are routed experts. As you lower rho, you explicitly remove MOE experts and reallocate those parameters to Engram embedding slots.
And when they swept that ratio across both a 5.7 billion and a 9.9 billion total parameter regime, the validation loss curve formed a very distinct U-shape.
Yeah, it proved that pure MOE is mathematically suboptimal. The sweet spot across both capacity regimes consistently lands at an allocation ratio of around 75 to 80%.
Wait, so you achieve a strictly lower validation loss by removing 20 to 25% of your dynamic MOE experts.
Yes.
And replacing them with static Engram embeddings.
Exactly.
Which completely upends the current conventional wisdom that we should just keep blindly adding routed experts. Scaling purely through conditional computation hits diminishing returns if you do not have a dedicated memory primitive.
Absolutely.
And here's where it gets really interesting. When you look at the benchmark results of the Engram 27B model built on this law, the performance gains are not isolated to knowledge-intensive trivia.
Intuitively, you expect MMLU to improve, and it does. It rises by 3.4 points. But the general reasoning benchmark, BBH, jumps by 5.0 points.
Yeah.
And in the code and math domains, Humaniville jumps by 3.0 points, and the math benchmark increases by 2.4 points.
But to understand why a static memory lookup table makes a model better at writing Python code or solving novel math problems, we really have to look at their findings in the infinite memory regime.
Right. They took a fixed 3 billion active parameter backbone and aggressively scaled the number of Engram embedding slots, adding up to 13 billion parameters of pure memory.
With 0 additional per token FLOPs.
Exactly.
And the validation laws exhibited a strict power law improvement, scaling linearly in log space. It proves that conditional memory is a distinct, scalable axis of sparsity.
But to answer why it improves deep reasoning in math, we really need to look inside the network using mechanistic interpretability tools, specifically logit-lens and centered kernel alignment.
Yes. Logit-lens basically projects each intermediate layer's hidden state with the final language modeling head to compute the callback libler, or KL, divergence against the final vocabulary distribution. Right, so a steeper descent in KL divergence means the model's intermediate states are confident about the output token much earlier in the network.
Exactly. And the Engram models exhibit a significantly steeper descent in KL divergence in the early blocks compared to the MOE baseline.
So it finishes feature composition much faster.
Because it is not wasting those early layers reconstructing static entities like Diana, Princess of Wales.
Right.
And they corroborated this using centered kernel alignment, or CKA, which measures the similarity of feature spaces between different networks.
So if we look at a heat map of the internal representations, we shouldn't see a one-to-one diagonal layer mapping between the MOE baseline and the Engram model anymore. We see the Engram model hitting higher levels of abstraction much earlier.
And that is exactly the physical manifestation we see. The CKA similarity heat map shows a massive upward off-diagonal shift.
Wow.
Yeah, the representations formed at layer 5 of the Engram 27B model are functionally equivalent to and align most closely with layer 12 of the pure MOE baseline.
That is incredible. By bypassing that early stage feature composition, Engram functions as a structural shortcut. It effectively deepens the network.
It does.
If your model reaches layer 12's level of abstraction by layer 5, you suddenly have 7 extra layers of computational depth freed up to focus entirely on complex reasoning, coding logic, and global context.
Which completely explains the results they achieved in long context retrieval. Because the attention mechanism is freed from managing local semantic dependencies, it can dedicate its capacity to tracking global context over massive sequences.
Oh, that makes so much sense.
Yeah, on the ruler benchmark, the multi-query needle in a haystack task jumped from 84.2 in the MOE baseline to 97.0 in the Engram model.
Huge jump.
And variable tracking went from 77.0 to 89.0. All because the model was not distracted by local memorization.
Okay, but as an ML engineer listening to this, you are probably looking at the hardware constraints. Memory bandwidth is already the primary bottleneck for LLM inference.
Oh, absolutely.
This math is elegant. But if we scale to a 100 billion parameter embedding table, hitting host DRAM over the PCIe should theoretically destroy our inference throughput. PCIe Gen 5 bandwidth is just a fraction of what you get from HBM3 on a GPU.
Yeah.
Hitting PCIe synchronously is normally a death sentence for latency.
It is the critical systems question.
Yeah.
But this is where the difference between Moi's dynamic routing and Engram's deterministic addressing completely changes the hardware paradigm.
I will say.
With a standard mixture of experts architecture, the routing is dynamic and sequential. You do not know which experts a token needs until that token's hidden state reaches that specific layer and passes through the routing linear layer.
Right. The routing decision depends on the computation of the preceding layers.
Exactly.
So Moi is kind of like a chef in a restaurant kitchen who doesn't know what spices to grab from the pantry until he finishes chopping the vegetables and tasting the sauce. You cannot prefetch the ingredients because the recipe changes based on the previous step.
That is a great way to put it. Engram, however, operates on input token IDs. The hash indices for the nagargrams depend solely on the input sequence.
Oh, wow.
Yeah, the moment the token sequence is known, before the forward pass even begins, the system knows exactly which embeddings it needs to retrieve.
Sticking with the kitchen analogy, then Engram is like having a prep cook with the full recipe card up front.
Yes.
Because the nagarm IDs are deterministic based on the input, the CPU can act as the prep cook. It queries the host DRAM over the PCI bus, fetching the ingredients, while the GPU, the chef, is still processing the dense computation for the very first transformer block.
It is pure asynchronous prefetching. You entirely decouple the parameter storage from the GPU's high bandwidth memory.
So by the time the GPU reaches the Engram layer, the memory is already waiting for it.
Exactly. The compute intensity of the early dense blocks masks the latency of traversing the PCIe bus.
And the empirical results on their inference harness back this up right. They took an NVIDIA H800 and attached an 8 billion parameter dense backbone to a massive 100 billion parameter Engram table offloaded entirely to CPU host memory.
Yep.
The end-to-end inference throughput penalty was only 2.8%.
At 2.8% overhead to access 100 billion parameters of factual knowledge is just remarkable.
It's unheard of.
And that was a conservative baseline, forcing all retrievals over PCIe. Natural language nulliograms inherently follow a Zipfian distribution, meaning the frequency of any pattern is inversely proportional to its rank.
Okay, so a very small fraction of patterns accounts for the vast majority of memory access.
Precisely.
Because of that Zipfian distribution, you can easily implement a multi-level cache hierarchy.
Exactly.
You pin the highly frequent critical patterns in the GPU's HBM L1 cache. You keep the moderately frequent patterns in the host DRAM L2 cache, and you just push the long tail of rare facts out to non-volatile NVMe SSDs.
It establishes infrastructure-aware efficiency as a first-class principle in model design. And the researchers actually proved that this structural separation of compute and memory is real through a targeted sensitivity ablation.
What do they do?
During inference, they completely suppressed the Engram module. They essentially lobotomized the model's static memory.
And the model's factual knowledge just collapsed, right?
On Trivia QA, performance dropped to just 29% of its original baseline.
Yeah, massive drop.
But tasks requiring deep contextual reasoning, like the C3 reading comprehension benchmark, retained 93% of their performance.
It is a clean, undeniable separation within a single neural architecture. The backbone attention handles the reasoning, and the Engram module handles the facts.
So what does this all mean? For you, the ML practitioner tuning the next generation of models, this fundamentally shifts how we view parameter allocation. The era of relying solely on scaling dynamic computation, just throwing more and more MOE experts at a problem, is evolving. It is. We are hitting a structural wall where simulating memory with compute is mathematically and physically inefficient.
The future lies in algorithm hardware co-design, where storage and compute are functionally decoupled.
If we connect this to the bigger picture, this research proves, both mathematically and empirically, that static retrieval is not just a relic of the NLP past.
Right.
When modernized with tokenizer compression, context-aware RMS norm gating, and deterministic hashing, conditional memory becomes a first-class modeling primitive. It is absolutely essential for pushing the boundaries of scaling efficiency.
Which brings us right back to where we started. That clean separation between the processor and the database in standard software systems. With Engram, we are finally bringing that engineering sanity back to large language models.
Exactly.
And it leaves us with a final, provocative thought experiment to ponder. If deterministic memory lookups can offload factual knowledge so efficiently to cheap host DRAM with less than a 3% latency penalty, What happens when we scale these static embeddings, not just to 100 billion, but to the multi-trillion parameter level?
Yeah, that is the million-dollar question.
Could the frontier models of tomorrow become vastly smaller in active compute-like, agile, reasoning-heavy processors that rely on massive, easily updatable, non-parametric solid-state drives acting as their primary world models? It's a completely different trajectory for designing intelligence. Thank you for joining us on this deep dive. We will catch you next time.